In this video, we are going to discuss electric flux. So recall that the electric flux is defined as the surface integral of the electric field over some area. So usually electric flux is denoted by phi, and it's a surface integral of an electric field vector over some area. So in general, this is quite a complicated mathematical object. And in this lecture, what we shall do is that we shall look into more detail about how to understand this. So let's start with a simple example. So consider a flat rectangular open surface. So here we have a flat rectangular open surface. And let's take a uniform electric field that is perpendicular to that surface. So let me imagine a uniform electric field, and this uniform electric field is perpendicular to this surface. This rectangular surface has an area A. So the area of this surface is A. And this is an example what I would call an open surface. So this is an example of an open surface. With an open surface, you can associate a vector to it. To see this, let's draw the open surface again over here. And let's draw a unit vector which is normal to this open surface. So this is the open surface, and the unit vector n makes 90 degrees angle to it. And then what we can do is that we can associate a vector A to this open surface whose direction is the same direction as the unit normal, but whose magnitude is equal to the area of that surface. This is a way of orienting surfaces in space. Not only do we know how big the area is, but we also know its orientation by the unit normal that is perpendicular to it. With this open surface, we could have drawn a different normal. We could have drawn a different normal in the opposite direction. So we see that if we had taken this other normal, say n hat prime, then we see that the area vector would be minus of the way that we have defined here. So for open surfaces, the definition of the area vector has some ambiguity in it. Now for our electric field through this area, let us choose the direction of the normal to be in this direction. Now what we want to do is to define the electric flux, which measures how much of this electric field points perpendicular to this surface. To measure how much a vector points perpendicular to a surface, we first need to define a normal vector to that surface, as we have done over here, and then we need to take the dot product between the electric field and that normal vector. So we have here the electric field E dotted with the normal vector N. Sometimes this is denoted by En. But for the electric flux, what we want is not exactly this. What we want is to multiply this quantity by the area of the open surface, and because this is just a scalar product, I can write this as E times dot An, and this is going to give me E dot A. And this is what we are calling the electric flux through this open surface. Now, it's important to do some examples. So let us look at some basic examples. So our first example we're going to take a uniform vector field. So it's important to remember that in these examples and in this lecture, the vector field is uniform. So this is our open surface. And what we take is, as our first example, a vector field that is at 90 degrees to the surface. And because it's a uniform vector field, we only have to draw it once. And then the dot product between this uniform vector field and the area vector is going to be E times dot n a, but the angle between E and n is 0, so this dot product just gives me E times a. So this is the flux for the case when a uniform electric field is perpendicular to the surface. Our second example will be the case where we have a uniform vector field, electric field, that is parallel to the surface. So this is the vector field E. And our normal vector is in that direction. So if I take the dot product between E and N, of course this is going to be 0 because this angle is 90 degrees. And therefore, if I take the dot product between E and the area vector, that is also going to be 0. So this is our flux for this second case. And for the third case, what we do is that we take the electric field to be in some arbitrary direction. So the electric field is pointing in some arbitrary direction. So this is E, and it's making an angle theta with the unit normal. In that case, the electric field dotted with the unit normal will give me E times cosine of theta. And in that case, the electric flux is given by E times A cosine of theta. So note that the first two cases, case number 1 and case number 2, are extreme cases of this guy, where in case number 1, the angle theta is 0, where case number 2, the angle theta is 90 degrees. So this is the simplest case of flux where the electric field was constant over the surface. Next, we shall look at the case where we have a more complicated surface and the electric field varies over the surface.